So integration by parts is used when we have two functions that are multiplied together, and one of the functions you can differentiate and the other function you can integrate. Another way of saying this is if you have something like u dv over dx like this here, so u and dv over dx are two functions and they're both multiplied together like this, and one of the functions you can differentiate, this is the u, and the other function you can integrate, and this is the dv over dx. And the integration by parts formula is given here. It is the integral of this u dv over dx, which is what we have here, is equal to uv minus the integral of v multiplied by du over dx. This is given to you in the formula booklet, so you have access to it in the exam. So that probably doesn't make too much sense on its own, especially this formula here. It looks really, really complicated. So let's go through an example to show how it works. So let's say that we need to integrate x cos x like this here. So we can use integration by parts on this because we have two functions that are multiplied together. One of the functions being this x here and the other function being this cos x. And a big clue for when we can use integration by parts is if one of the functions is x like this here. This is a really, really big clue that we can use integration by parts. So the way that we're going to solve this is we're going to call one of the functions u, and we're going to differentiate this function, and we're going to call the other function dv over dx, and we're going to integrate this function. So what function do we call u and what function do we call dv over dx? Well, like I said before, with one of the functions being x, we usually call this one u, and we normally differentiate the x, and then we normally call the other function, so in this case the cos x, the dv over dx, and then we integrate this. It's not always like this, and we'll go through examples in this video of when it's the other way around, but in this case it is like this. Okay, so we've called u x like this here, so what we're going to do is we're going to differentiate this. So it's going to be du over dx if we differentiate this, and this is equal to, and then when you differentiate x, it's just 1 like this here. Okay, and then we've got this dv over dx is equal to cos x, so we're going to integrate this. So if we integrate this dv over dx, it's going to be v, and then this is equal to, and then when you integrate cos of x, we've already talked about this in this chapter in year 2 integration, when you integrate cos of x you get sin of x like this here. And then what we're going to do is we're going to plug these into this formula up here. Okay, so this here, this x cos of x here, is equal to uv, and u here is x and v is equal to sin x, so therefore uv is equal to x sin x like this here, and then it's going to be minus the integral of v du over dx. So v is this sin x here, and du over dx is this 1 here, so therefore v du over dx is going to be sin x multiplied by 1, which is just going to be equal to sin x. So it's going to be the integral of sin x and then this dx on the end like this here. So we've written it in this format here for the integration by parts, and what we can do is we can simplify this because we have this integral of sin x like this here, and we've talked about in this chapter already that when you integrate sin x you get minus cos x like this here, and as we've integrated we need to include this plus c on the end, remember the constant of integration, and then we can simplify this again because we've got this minus minus like this here, so these just cancel out and leave us with this here, which is x sin x plus cos x, and then this plus c on the end, and this here is the answer. We've done integration by parts. The integral of x cos x is equal to this here. So what we've essentially done with integration by parts is we've converted something that can't be directly integrated, like this x cos x here, and we've converted it into something that can be directly integrated, like this sin x here, and that's how integration by parts works. So as I've already mentioned, there are clues for when you can use integration by parts, the big one being that if you have two functions like this multiplied together. Another big clue is if one of the functions is x here, and then you call that u, and then you differentiate it, and then you call the other function the dv over dx, and then you integrate that. However, there are examples that are not of this format here, and we'll go through examples like that in this video. So here's another example. I'm going to leave up the formula for integration by parts for the entire video because, as I said, it's given to you in the formula booklet, so you have access to it in the exam. So for this one here, we have to integrate x e to the power of x. So we have these two functions multiplied together, this x and this e to the power of x, and one of the functions is x. So this is quite a big clue that we need to use integration by parts. So what we're going to do is going to call one of them u and one of them dv over dx, and as I mentioned before, we normally call x u, and then the other function we normally call the dv over dx, so we're going to call this e to the power of x. So if we differentiate this, u is equal to x, it's going to be du over dx is equal to, and then when you differentiate x, it's 1, and then we're going to integrate this dv over dx is equal to e to the power of x, so it's going to be v is equal to, and we've talked about in year 2 integration already, that when you integrate e to the power of x, it's still just e to the power of x, it doesn't change. So therefore we're going to use this formula here. So this formula is it's equal to uv, so u is equal to x and v is equal to e to the power of x, so uv is going to be x e to the power of x like this here, and then it's minus the integral of v du over dx. So v is this e to the power of x and du over dx is 1. So 1 multiplied by e to the power of x is just e to the power of x. So it's going to be minus the integral of e to the power of x like this here, and then dx. And we can simplify this because, as we've already said, when you integrate e to the power of x, it's still just e to the power of x like this here. And remember this plus c on the end. So this is the answer here. The integral of x e to the power of x is equal to x e to the power of x minus e to the power of x, and then remember the plus c. Okay, so here's another example where we need to integrate 4x sec squared of x, like this here. So we have this 4 coefficient at the front, and what we can actually do is just take this out of the integral, like this here, and then just focus on integrating this, and then just multiply the entire thing at the end by 4. So we need to integrate this x sec squared of x here. So we have these two functions multiplied together, and again, one of them is x. So what we're going to do is we're going to call u x, and we're going to call this sec squared of x the dv over dx. So therefore, if we differentiate this, u is equal to x like normal, it will be du over dx is equal to 1. And then if you integrate this dv over dx is equal to sec squared of x, it's going to be v is equal to, and we've already talked about in year 2 integration, that when you integrate sec squared of x, it's equal to tan of x. This is actually also given to you in the formula booklet. So therefore, v is going to be equal to tan x. So therefore the integration by parts formula is going to be uv, which is x multiplied by tan of x, so it's going to be x tan x like this here, minus the integral of v multiplied by du over dx, so it's going to be tan x multiplied by 1, which is just going to be tan of x like this here. And remember, we need to multiply the entire thing by 4 like this here. So we need to integrate tan of x like this here, and if you don't know, it's kind of excusable if you don't know, it kind of doesn't come up much, but the integral of tan x is actually given to you in the formula booklet. The integral of tan x is equal to the natural log of the modulus of sec x like this here. So therefore we can write this like this here. So this is given to you in the formula booklet, and therefore if you want to, you can expand through this 4 like this. So it's equal to 4x tan of x minus 4, and then the natural log of the modulus of sec x, and then remember this plus c on the end. Okay, so here's another example where we need to integrate between the limits of 1 and 4 x natural log of x, and we need to give our answer in the form a natural log of 2 minus b. So we need to find what a and b are. So we've talked about this before with definite integrals. These limits here, 1 and 4, at the beginning of the question we don't actually need to worry about these. We're going to plug these into the answer at the end. What we first need to do is actually focus on this integration. So let's first focus on integrating this x natural log of x. So this is of the format that we've seen before because one of the functions is x. So therefore you might be tempted to use the approach we did before and call u x and then differentiate this and then call the other function, which in this case is the natural log of x, call this dv over dx and then integrate this. The only issue with this is we haven't actually learnt yet how to integrate the natural log of x. We're actually going to talk about it in this video, how to do it, but it's not that simple. It's quite complicated, and therefore we don't really like calling dv over dx natural log of x and then integrating this. However, what we do know how to do is we do know how to differentiate the natural log of x. We've talked about this already in this chapter. So in this particular instance, what we're actually going to do is we're going to switch it around, and instead we're going to call u the natural log of x and differentiate this, and we're going to call dv over dx x in this case, and we're going to integrate this. So we've swapped it around in this case. So if we differentiate this, u is equal to the natural log of x, it's going to be du over dx is equal to, and then when you differentiate the natural log of x, we talked about this already in this chapter, we also talked about it in year 2 differentiation, so go back to that if you need a reminder. When you differentiate, the natural log of x is equal to 1 over x, and then if we integrate this here, it's going to be v is equal to, and then when you integrate x, we talked about this in year 1 integration, this is just basic integration, when you integrate x, it's equal to half x squared. So therefore, if we use this formula down here, it's going to be uv, so u is equal to the natural log of x and v is equal to half x squared. So uv is going to be equal to half x squared natural log of x, and then this is going to be minus the integral of v du over dx. So v is equal to this half x squared and du over dx is equal to 1 over x. So v du over dx is half x squared multiplied by 1 over x, and then we can simplify this because we have this x squared multiplied by 1 over x, so this x here will cancel out with one of the x's here and just leave us with half x like this here. So therefore this is going to be minus the integral of v du over dx, so it's going to be minus, and then I've taken the half out of the integral here, minus half and then the integral of this x here. So this is the integration by parts formula here. And then we can simplify this because the integral of x here, as we've already mentioned, is equal to half x squared, like this here. And then remember, we need to multiply this by the minus a half that we took out at the start. So minus a half multiplied by a half is equal to minus a quarter, like this here. So therefore, the integral here is half x squared, natural log of x, minus a quarter x squared. And then remember the plus c on the end. So now what we need to do is actually plug in these limits of 1 and 4 into this function here. So if we start with the 4, it's going to be half and then 4 squared, and then the natural log of 4 minus a quarter 4 squared, like this here. And then it's going to be minus, and then we plug the 1 in, so it's going to be half 1 squared, and then the natural log of 1 minus a quarter 1 squared, like this here. And we can simplify this because we have this natural log of 1 here, and natural log of 1 is 0, so therefore this term is going to cancel out. So if we simplify this further, 4 squared is equal to 16, and then 16 multiplied by half is 8, so this term here is going to be 8 natural log of 4, and then this 4 squared is 16, and then when you multiply it by this minus a quarter, it's going to be equal to minus 4, like this here. And then this 1 squared is just 1, so it's going to be minus a quarter here, but we're going to multiply it by this minus at the front here, so it's going to be equal to plus a quarter, like this here. And then minus a 4 plus a quarter is equal to minus 15 over 4, like this here. So this b here is equal to 15 over 4. Now this term here is a bit more complicated because here we've got 8 natural log of 4, but we need this in the form a natural log of 2. So we haven't got the correct form of the natural log here. We need it as the natural log of 2. And we can write this in the correct format because if you consider 8 of the natural log of 4, well, we can write 4 as 2 squared, like this here. And then if we've got a power in a log, remember that we can bring this to the front of the log. So this becomes 8 multiplied by 2 natural log of 2, like this here. And then 8 multiplied by 2 is 16. So we can write 8 natural log of 4 as 16 natural log of 2, like this here. And therefore we've got this in the correct format now of this a natural log of 2. So therefore a is equal to 16. So therefore that's the final answer, where a is equal to 16 and b is equal to 15 over 4. Okay, so here's another example where we need to integrate x squared multiplied by e to the power of x, and this is a really interesting example. So we're going to use integration by parts because we have these two functions that are multiplied together, but which one are we going to call u and which one are we going to call dv over dx? So what we're going to do is we're going to call u the x squared, and we're going to differentiate this, and we're going to call the other function, which in this case is the e to the power of x, we're going to call this the dv over dx, and then we're going to integrate this, and you'll see in a moment why we've done it this way. So if we differentiate this, u is equal to x squared, it's going to be du over dx is equal to, and then when you differentiate x squared, this is just basic year one differentiation, this is equal to 2x, and then when you do the dv over dx is equal to e to the power of x and integrate it, it's going to be v is equal to, and as I've already talked about in this video, when you integrate e to the power of x, it's still just e to the power of x, like this here. So if we use the formula for integration by parts down here, it's going to be uv, so u is x squared and v is equal to e to the power of x, so uv is x squared e to the power of x, and then it's going to be minus the integral of v du over dx. So v is equal to e to the power of x and du over dx is equal to 2x, so this is going to be minus the integral of 2x e to the power of x. I've taken this 2 out of the integral like this here, so we have the integral of x e to the power of x like this here. So we've done the integration by parts here, but you can see actually that this x e to the power of x, we cannot actually directly integrate this yet. What we're actually going to do is we're going to do integration by parts again on this x e to the power of x, and this is kind of the standard format where x is one of the functions, and we're going to do it the way that we normally do it. We're going to call x in this case the u, and we're going to call dv over dx the e to the power of x. So when you differentiate this here, it's going to be du over dx is equal to, then when you differentiate x, it's equal to 1, and then dv over dx is equal to e to the power of x. So when you integrate this, it's v is equal to, and again it just remains as e to the power of x. Now when we're doing this, remember that you need to keep this part here the same, so we still have this x squared e to the power of x minus 2, and then we are integrating this here by parts, so like this here. So this is inside a minus 2 bracket, so it's going to be integration by parts is uv, so u is equal to x and v is equal to e to the power of x, so uv is x e to the power of x, and this is going to be minus the integral of v multiplied by du over dx, so v is e to the power of x and du over dx is equal to 1, so 1 multiplied by e to the power of x is just e to the power of x, so it's minus the integral of e to the power of x like this here. And as we've already talked about, when you integrate e to the power of x, it's still just e to the power of x like this here, and then remember the plus c on the end, and then we can simplify this because we can expand this minus 2 bracket here, so minus 2 multiplied by x e to the power of x is minus 2 x e to the power of x, and then minus 2 multiplied by this here, this minus will cancel out with this minus, so we're left with plus 2 e to the power of x like this here, and then remember the plus c. So this here is the final answer. If you wanted to, because e to the power of x is common in all the terms, you could make it a bit neater by factorising out the e to the power of x, so it's e to the power of x multiplied by x squared minus 2x plus 2, and then plus c, but you don't have to do this, it's not asked as part of the question. But this is a really interesting example. We actually integrated by parts twice. We did it the first time to make this x squared and x like this here, and then we did it the second time to remove this x here to make it the integral of e to the power of x. So this is quite common. If you see x squared as part of the integral, this is a sign that you might need to integrate it by parts twice to do it like this here. Okay, so here's a really interesting example that's quite commonly asked, where we need to integrate the natural log of x. This is also mentioned on the specification as an example that they could mention to you, and I'd maybe try and remember how this one works because it's quite a weird method for the way you have to do it. So at first it looks really odd that we can do this by integration by parts, because it looks like we only have one function, which is the natural log of x, and not these two functions that are multiplied together that we need for integration by parts. And the key to this is we're going to rewrite this integral here, the integral of the natural log of x, as the integral of 1 multiplied by the natural log of x. And when we do this, we have now technically got two functions multiplied together, this 1 and this natural log of x here, and therefore we can use integration by parts and call one of these u and one of these dv over dx. So the question is, what way around are we going to do it? Well, we've kind of talked about this before. We don't really want to call the natural log of x dv over dx, because that means that we're going to have to integrate this. So we're going to have to integrate the natural log of x, and as we talked about before, we don't really know how to integrate the natural log of x. We can't do it directly. So what we're going to do is we're going to call the natural log of x u, like this here. So we're going to differentiate this, and therefore we're going to call the 1 the dv over dx, and we're going to integrate this. So if we start with this and we're going to differentiate this, it's going to be du over dx is equal to, and as I've already mentioned, when you differentiate, the natural log of x is equal to 1 over x, like this here from year 2 differentiation. And then if we integrate this here, this dv over dx, it's going to be v is equal to, and then when you integrate 1, this is just basic year 1 integration. When you integrate 1, it's just equal to x, like this here. So if we use the formula for integration by parts, it's going to be uv, so u is equal to the natural log of x and v is equal to x, so uv is going to be x and then the natural log of x, and then this is going to be minus the integral of v multiplied by du over dx. So v is equal to x and du over dx is equal to 1 over x. So that means that v du over dx is going to be equal to x multiplied by 1 over x, and this is going to cancel out. This x is going to cancel out with this x here, and it's just going to leave us with 1. So therefore v du over dx is just going to be 1, so it's going to be minus the integral of 1 and then dx, like this here. And we can do this integral here because the integral of 1 of dx, when you just integrate 1, like we said here, it's just equal to x, like this here, and then remember the plus c on the end. And then this is the answer here to the integral of the natural log of x. Is equal to x natural log of x minus x and then plus c, like this here. Now, as I mentioned, this comes up a lot and it's mentioned on the specification as an example that they could ask you. So I'd maybe remember how to do this one. Try and remember at the start that we need to convert this natural log of x to 1 multiplied by the natural log of x, and then do integration by parts. So here's another interesting example where we need to integrate e to the power of x sin x. Now, when I was at A level, I actually got asked this question in a practice exam and I couldn't do it at all and I got really frustrated. And the reason is because the method for this example is really weird and quite unusual. So much so that, kind of similar to the last example, I would maybe recommend remembering certain parts of it so you don't get caught up in the same way that I did. And one particular thing you have to do with this example is, so the integral is e to the power of x sin x dx, and what we're actually going to do is we're going to say that capital I is equal to this. So capital I is equal to the integral of e to the power of x sin x dx, and as we go through this method you'll see why we need to do this label like this here. Okay, so if we do this, we can do integration by parts because we have two functions that are multiplied together. So which one do we call u and which one do we call dv over dx? Well, in this particular example, it doesn't actually matter which one you call u and which one you call dv over dx. They'll both lead to the same conclusion and the same problem. So let's just say that u is equal to sin x, and therefore the other function e to the power of x is equal to dv over dx. Okay, so if we differentiate this here, it will be du over dx is equal to, and then when you differentiate sin x is equal to cos x, and then if you integrate this here, it's going to be v is equal to, we've already talked about that when you integrate e to the power of x, it's still just e to the power of x. So the integration by parts formula is uv, so u is equal to sin x, and v is equal to e to the power of x, so uv is e to the power of x sin x, minus the integral of v du over dx, so v is e to the power of x, and du over dx is cos x, so this is going to be minus the integral of e to the power of x cos x, like this here. So we've done the integration by parts formula here. Now the issue is this integral that we've got out here, this e to the power of x cos x, we can't integrate this directly. And because we've got these two functions that are multiplied together, this integral here, what we can actually do is we can do integration by parts again. So we can call one of these u and one of these dv over dx, these two functions here. And similar to the previous one, it doesn't matter which one we call u and which one we call dv over dx, they both lead to the same conclusion. So let's just say that u is equal to cos x and dv over dx is equal to e to the power of x. So therefore, if we differentiate this, it would be du over dx is equal to, and then when you differentiate cos x is equal to minus sin x, remember the minus at the front, and then when you integrate this here is v is equal to, and again when you integrate e to the power of x it's still just e to the power of x like this here. So remember, we need to keep this e to the power of x sin x minus part because this was from the previous integration by parts, and now we're integrating this here by parts, so this is going to be uv, so u is cos x and v is e to the power of x, so it's going to be e to the power of x cos x, and then it's going to be minus the integral of v du over dx, so v is equal to e to the power of x and du over dx is equal to minus sin x, so this is going to be minus the integral of minus e to the power of x sin x. Be careful with the minuses here because you have this one here as well, and then we can simplify this because we have these two minuses here that are going to cancel out and leave it with a plus like this here, and then we can simplify this further because we have this minus at the front with this bracket, because remember this is minus this integral here, so this minus will be affecting this entire bracket here, so this will become minus e to the power of x cos x minus the integral of e to the power of x sin x like this here. So we've got this expression here, but here we've kind of created a really weird problem because now we have the integral of e to the power of x sin x, and you can see that this is actually what we started with as well, this e to the power of x sin x. So we've got this really weird situation where we've integrated twice by parts, we've actually done quite a lot of work, and we've actually ended up with the exact same thing that we've started with. Okay, so what have we actually done so far? Well, what we've done is we've tried to solve this integral of e to the power of x sin x, and we've integrated by parts twice in order to get this really weird expression here that's got its own integral inside it. So what do we do now? Well, now what we're going to do is we're going to make use of this capital I is equal to the integral of e to the power of x sin x dx, and what we're going to do is with this equation here, we're going to sub out all of the times this integral comes up, and we're going to sub it out for a capital I. So where does this integral come up? Well, it comes up here, this integral of e to the power of x sin x dx, so we're going to sub this out for a capital I. And it also comes up here as well, this integral of e to the power of x sin x dx, so we're going to sub this out for a capital I as well. So therefore we can rewrite this equation here as capital I is equal to e to the power of x sin x minus e to the power of x cos x and then minus I. And then what we can do is bring this minus I onto the other side of the equation, so it becomes 2 capital I is equal to e to the power of x sin x minus e to the power of x cos x, and then we can divide both sides by 2, so this 2 on this side goes away, so it becomes capital I is equal to half e to the power of x sin x minus e to the power of x cos x, and then we can sub out this capital I and we can sub back in this integral here to get that the integral of e to the power of x sin x dx is equal to this here, and this here is the answer. The integral of e to the power of x sin x dx is equal to this half e to the power of x sin x minus e to the power of x cos x, and then remember a plus c on the end. What you can also do is, because e to the power of x is present in both the terms, you can factorize this out and write it as e to the power of x over 2 sin x minus cos x like this, and then plus c. So I think this method is really weird because it doesn't really feel like we've actually done any integration, but we've integrated it by parts twice, and we've shown that this integral here is equal to this answer here. So the way that you do this is integrate it by parts twice in order to get this weird kind of equation here, and then you make use of this substitution in order to get this here as the final answer. Okay, so here's a couple of past paper questions for you to have a go at. So pause the video, have a go, and I'll go for the answers in about 5 seconds. Okay, so for question 1a, we're told that f theta is equal to 4 cos squared theta minus 3 sin squared theta, and we need to show that this can be written as half plus 7 over 2 of cos 2 theta. Now, I think there's a couple of ways that you can do this question, but I think the easiest way is to consider the double angle formula that cos 2 theta is equivalent to 2 cos squared theta minus 1, and that cos 2 theta is equivalent to 1 minus 2 sin squared theta. Go back to the videos on the double angle formula if you need a reminder of how these work. And then what we can do is rearrange these in order to make cos squared theta and sin squared theta the subject, and then just sub these in for this here in order to get an expression for this cos 2 theta here. So if we start with this here, if we move the minus 1 onto the other side, we get that cos 2 theta plus 1 is equivalent to 2 cos squared theta, and then we divide both sides by 2, we get that half cos of 2 theta plus a half is equivalent to cos squared theta. So here we can sub out the cos squared theta for this here, and then for this one here it's pretty much the exact same. Move the 1 onto the other side to get this, and then divide both sides by minus 2 to get that half minus a half cos of 2 theta is equivalent to sin squared of theta. So if we sub this in, it's going to be 4, and then rather of cos squared theta, it's going to be this half cos of 2 theta plus a half, and then it's going to be minus 3, and then instead of this sin squared theta, it's going to be this half minus a half cos of 2 theta like this here. We can simplify this because 4 multiplied by a half is 2, and 4 multiplied by a half here is also 2, and then minus 3 multiplied by a half here is going to be minus 3 over 2, and then this minus 3 multiplied by this minus half is going to be plus 3 over 2 like this here. And then we've got this 2 cos of 2 theta plus 3 over 2 cos of 2 theta, which is equal to 7 over 2 cos of 2 theta. And then we've got this 2 minus 3 over 2, which is equal to a half. And this is what's required, this half plus 7 over 2 cos of 2 theta. Okay, and then for part B, we need to find the exact value of the integral between 0 and pi over 2 of theta f theta. Now, as we showed in part A, the f theta can be written as half plus 7 over 2 cos of 2 theta. What this question is asking us is to find the exact value of the integral between 0 and pi over 2 of theta, and then we can sub out this f theta for this here, so it's half plus 7 over 2 cos of 2 theta. So we need to find the exact value of this integral here. Now, this is a definite integral, and as I talked about before with definite integrals, you don't need to worry about these limits at the start. We plug these in at the end. We firstly need to focus on the actual integration, so we need to integrate this theta and then half plus 7 over 2 cos of 2 theta. So in order to integrate this, we're going to expand this bracket. So we're going to do theta times a half, which is a half theta, and then theta multiplied by this here. So it's going to be 7 over 2 theta cos of 2 theta. So now we need to integrate this here. So we have these two terms I've talked about before. When you're integrating multiple terms, you just consider the terms individually. So if we start with this half theta here, I've taken the half out of the integral, so it's half and then the integral of theta d theta. This is just basic year one integration. When you integrate theta in terms of d theta, is equal to half theta squared like this here. Then remember, we need to multiply it by the half at the front, so half multiplied by half is a quarter theta squared like this here. So that's what happens when you integrate this half theta. And now we're going to consider what happens when you integrate this 7 over 2 theta cos of 2 theta. Again, I've taken the 7 out of 2 out of the integral. So we're integrating this theta cos of 2 theta. So we have these two functions multiplied together, the theta and cos 2 theta. So we can use the integration by parts. And we're going to use integration by parts because if you want to write this in terms of x, this is x cos of 2x dx, and you can see that we have this x function here that we like to call u and differentiate this. So that's what we're going to do. So if we're working in terms of theta, we're going to say that u is equal to theta here, and dv over d theta this time, because we're working in terms of theta, not x, dv over d theta is equal to the other function, which is this cos of 2 theta. Okay, so if we differentiate this, u is equal to theta here, it's going to be du over d theta this time is equal to, then when you differentiate theta, it's equal to 1, and then if you integrate this here, it's going to be v is equal to, so when you integrate this here, when you integrate cos, it's equal to sin, but remember, when you integrate cos of 2 theta, you also need to divide by this 2 here, so it's going to be half sin, and then this 2 theta is still going to be like this here. So the integration by parts formula is uv, so u is theta and v is half sin of 2 theta, so it's going to be half theta sin of 2 theta. Remember, we also need to multiply the whole thing by this 7 over 2 here that we took out, and then it's going to be minus the integral of v and then du over dx, although this time it's going to be d theta instead. So v is equal to half sin of 2 theta, and du over d theta is equal to 1, so therefore if you multiply this together, it's just going to be minus the integral of half sin of 2 theta, but again I've taken this half out of the integral like this here. So we've got this integral of sin of 2 theta, and when you integrate sin of 2 theta, when you integrate sin, it's going to be minus cos, remember, and then we also need to divide by this 2 here, so it's going to be equal to minus a half cos of 2 theta when you integrate this sin of 2 theta. We can simplify this because we've got this 7 over 2 multiplied by this half here, so this is going to be 7 over 4, and then we've got this minus a half times minus a half, which is going to be equal to a quarter, which is then going to be multiplied by this 7 over 2, so this is going to be equal to 7 over 8 altogether. So the final answer when we integrate this by parts is 7 over 4 theta sin of 2 theta plus 7 over 8 cos of 2 theta. So that's what happens when you integrate this term here. So overall, this whole thing integrated is going to be these terms added together. So it's going to be a quarter theta squared, and then it's going to be plus 7 over 4 theta sin of 2 theta plus 7 over 8 cos of 2 theta, and then remember the plus c on the end. Okay, so we found what the integral is, so now we need to sub in these limits of 0 and pi over 2 into this kind of really horribly long expression here. So if we do that, so if we start with pi over 2, it's going to be this, and then it's going to be minus, and then if we sub in 0, it's going to be this. I won't go through saying what each term is, just kind of trust me that this is what it is, because it's a really, really long expression. So therefore what we can do is we can cancel some stuff down here, because here we've got a 0 squared, so this is going to cancel out and be 0. Here we've got something multiplied by 0, so it's going to cancel out. Here we have got sin of pi, which is equal to 0, so this is going to go away as well. So the terms that we're left with is this quarter multiplied by pi over 2 squared. Pi over 2 squared is going to be pi squared over 4, and then if you multiply this by the quarter, it's going to be pi squared over 16. And then this term here, cos of pi is equal to minus 1, so this here is going to be minus 7 over 8. And then cos of 0 is equal to 1, so this is going to be 7 over 8, but remember we're minusing this, so it's also going to be minus 7 over 8. And then minus 7 over 8 minus 7 over 8 is equal to minus 7 over 4. So this is the final answer. This is the exact value of this integral here, pi squared over 16 minus 7 over 4. Okay, and then for question 2, we need to show that the integral between 1 and e to the power of 2 of x cubed multiplied by the natural log of x is equal to ae to the power of 8 plus b. And we essentially need to find what a and b are. Okay, so as I talked about before with definite integrals, we don't need to worry about these limits at the start. We're going to sub these in at the end. What we first need to focus on is integrating this x to the power of 3 natural log of x. So if we do this, we can use integration by parts because we've got two functions that are multiplied together. So what do we call u and what do we call dv over dx? Well, we've kind of talked about this already in this video. We don't want to call dv over dx the natural log of x because that means we're going to have to integrate the natural log of x. And even though we've actually talked in this video about how we do it, it's quite complicated to do. We kind of want to avoid doing it. So what we're going to do to avoid this, we're going to say that u is equal to the natural log of x, so we can differentiate it instead, and therefore we're going to say that dv over dx is equal to x to the power of 3 instead. So therefore, if we differentiate this u is equal to the natural log of x, it's going to be du over dx is equal to, when you differentiate the natural log of x, is equal to 1 over x, and then if we integrate this here, it's going to be v is equal to, and then when you integrate x to the power of 3, this is just year 1 integration, it's equal to 1 over 4 x to the power of 4. So therefore, using the formula for integration by parts, it's uv, so u is equal to the natural log of x, and v is equal to a quarter x to the power of 4, so uv is going to be a quarter x to the power of 4 natural log of x, and then this is going to be minus the integral of v du over dx, so v is equal to this quarter x to the power of 4, and du over dx is equal to 1 over x, so if we multiply them together, it's going to be a quarter x to the power of 4 multiplied by 1 over x, and then x to the power of 4 multiplied by 1 over x is going to be x to the power of 3, so therefore this can be written as 1 over 4 x to the power of 3, so therefore this is going to be equal to minus the integral of this quarter x to the power of 3. I've taken the quarter out of the integral like this here, and then we can simplify this because the integral of x to the power of 3, as we've already mentioned, is a quarter x to the power of 4, and then if we multiply this by the minus a quarter that we took out, so minus a quarter multiplied by a quarter is minus 1 over 16 like this here, so therefore this integrated is a quarter x to the power of 4 natural log of x minus 1 over 16 x to the power of 4, and then remember the plus c on the end. So we've shown that the integral is equal to this here, so now we need to plug in the limits of 1 and e squared. So if we do that, so first let's focus on this e squared, so it's going to be a quarter and then e squared to the power of 4 instead of x to the power of 4, and then the natural log of e squared, and then it's going to be minus 1 over 16 e squared to the power of 4 like this here, and then it's going to be minus, and then we're going to sub in 1, so it's going to be a quarter 1 to the power of 4, the natural log of 1 minus 1 over 16, 1 to the power of 4. So we can simplify this because natural log of 1 is 0, so therefore this term will just go away. This term here I'm going to write up here because it's quite complicated the way that we have to simplify it. So firstly, we have this e squared to the power of 4, which is going to be equal to e to the power of 8 like this here, and then we have this natural log of e squared. And remember, when you have a power inside a log, you can take the power and bring it out of the log and put it as the coefficient, so therefore we can write this natural log of e squared as 2 natural log of e, and we can simplify this further because 2 multiplied by a quarter is equal to a half, so it's half e to the power of 8, and remember that the natural log of e is equal to 1, so this will just go away, so therefore this is just equal to half e to the power of 8 like this here, and then this term, this minus 1 over 16 e to the power of 2 to the power of 4, this will be e to the power of 8, so it's going to be minus 1 over 16 e to the power of 8, and then this over here, 1 to the power of 4 is just 1, so it's going to be minus 1 over 16, but remember we have a minus here as well, so these two minuses are going to cancel out and leave us with plus 1 over 16, and then we can simplify this because half e to the power of 8 minus 1 over 16 e to the power of 8 is 7 over 16 e to the power of 8, and therefore this is in the correct format up here. So therefore a is equal to 7 over 16 and b is equal to 1 over 16.